Going to look at some important examples of vector fields. These are examples I keep coming back to over and over again when I teach this because some of them are really crucial, and then some of them are just good examples of how vector fields work and how plotting vector fields work. So we're going to start out, in this video, we're just going to look at vector fields in the plane. I'll do a follow-up with a few 3D examples. So we're in R2, we're in the plane. Let's let R be the usual radial coordinate. Square root of x squared plus y squared, the distance from a random point to the origin. And I want to start out with a very important vector field called the radial vector field. And it's xi plus yj. And I claim it looks like this. So let me go to the by hand picture. I'll just talk real briefly about how you would plot something like that by hand. Well, the idea is a little tedious, but the idea is somewhat similar to plotting a function. You select a bunch of inputs, figure out what those inputs give, and then see what that picture results in. The difference here is we can't pick sort of all possible input points for a vector field and draw an arrow at every one of those points, because then the whole thing would just be all ink. So we usually plot some sort of regular grid. So maybe like it's up to exactly the details of the problem. We might pick the integer points, for example, and plot arrows at every one of those grid points. And that's what the vector field plotter I'm going to show you in a minute does. So for example, if we're at the point 2, 3, if x is 2 and y is 3, then we're going to get r at the point 2, 3. Well, there's something very special about this particular vector field. It's 2i plus 3j, or often written, like in Stewart's book, 2, 3 with angle brackets. That's the vector that goes exactly this much to the right and this much up. And so it's going to be placed here. So remember, an important thing about a vector field is that this vector is going to be living right here. But it's going to be going exactly the same as if we took the position vector, take this coordinate pair, turn it into a vector, but then make sure its base point is at the right place. So a good way to picture that is take that arrow connecting the origin to that dot and then put it right here. And what are you going to have? You have something that's always pointing directly outward from the origin, and the magnitude of this guy, well, this is just exactly the coordinates of that point put into vector form. It's just going to be the square root of x squared plus y squared, which is just r, which is the distance from the origin. So, for example, like 1 comma minus 1, it will be this arrow translated here. So again, it'll be pointing directly radially outward, and it's smaller because this was a point that's closer to the origin. Now, if we just did that for a whole bunch of grid points, we would get a picture of this thing. Now, one thing about plotting vector fields that's important is if you plot the arrows too big, let me just quickly plot a bad version of this. You're going to have them overlap a bunch. And you might have something that's a real mess with the arrows all overlapping each other. It's almost always totally permissible to scale down the arrows. And it's helpful if you actually tell people that you're scaling them down like that, but sometimes it's not even explicit that you scale them down. So it wasn't absolutely necessary for me to draw this exactly as long as this length, because it might be a better picture to scale it. There's another reason why that's actually totally legitimate. It's extremely rare. It could happen, but it's pretty rare that the units for the vectors that you're actually drawing are really the same as the units of length. So these guys, vector fields, are often describing flows, in which case they're velocities or maybe accelerations, or their forces, or their electric field strengths or magnetic field strengths. None of those are in units of meters or units of length. And so it actually doesn't really mean anything to say this length should be exactly the same as this guy. Mathematically, if we're doing this version, then theoretically this really should be exactly this length, but it's not a big deal. You shouldn't scale them arbitrarily, though. You should pick some global scaling and be true to that global scaling. So, for example, with this picture, if you can see the numbers here, x is going 2, 4, so x is like 5 here, and maybe y is 2. This is right around here is like 5, 2. The arrow there, theoretically, is a lot longer than these arrows being shown here. So it is auto-scaled to make sure that the arrows are not long compared to the scaling, the grid scaling, and so they hardly ever overlap each other at all. And that's automatically done by most vector field plotters. And that's totally legal. So here's what the computer does. Oh, notice these little V guys. That's arrowheads, so they accurately indicates the direction. But the fact that there's no tail, or the length of the tail, the shaft here, is very small, indicating that's a very small vector right there. And then here, it's much longer. Okay, so xi plus yj is the radial vector field because it's always pointing in the radial direction. You always want to think of vector fields. The two main models of vector fields are flows of fluids. There's many other things that are described by vector fields, but the two ones to think of is the flow of a fluid, so that this is going to be the velocity vector of a particle of that fluid at that point. And for us, usually we're going to think of like a steady state flow or a snapshot at an instant of a flow. So it's not something that varies with time. That just makes things simpler. And then you can try to think of any vector field as a force field, so that this is the force due to some force like electricity, magnetism, something like that, or gravity, exerted on some sort of test particle that would live at this point. Well, this particular vector field is a funky thing in terms of flows, because you notice it sort of looks like there's stuff flowing outward. You might say maybe there's a source at the origin, but notice the vectors are very, very small here. So there's very little stuff actually flowing out here. Like if you drew a circle right around here, there's actually very little flowing out. Whereas if you draw a circle out here, there's a lot more flowing out. So you can picture this as a flow of a fluid with tiny little point sources everywhere in the plane. So maybe if like this is a piece of fabric that's on fire, and every little piece of the fabric is producing smoke, then that smoke might billow out in this pattern. I like to picture like an air hockey table with little tiny pinpricks that let in water or air or some fluid onto the table. And if they're uniformly distributed and they're all pumping out fluid at the same rate, you might get this kind of picture if the fluid goes radially outward, which it doesn't absolutely have to, but if it happened to be going radially outward, that's consistent with the idea there's a source everywhere uniformly. So it's a little bit weird as a flow. As a force field, it's actually even stranger, that it's always pointing outward and getting stronger as you go away from this central point. This kind of looks like the central point is doing something, like it's like a repulsive electric thing, but it wouldn't get stronger as you go out. So even though this is mathematically a good place to start, it's actually not, it's a little bit weird as a flow and not really something you want to think of as a force field. The magnitude is always important. And as I pointed out, the magnitude of these arrows is just equal to the radial coordinate. Okay. For any vector field, you want to ask some qualitative questions. Is it continuous? Is it differentiable? And by that, we just are going to mean that the component functions are differentiable. And even more special is when it's linear. And indeed, both of these functions are just linear functions of x and y. So this is a linear vector field, and those are always continuous and differentiable. Okay, so let's look at the next one. We're going to take the vector field r and we're going to divide it by the radial function r, the scalar function r. So the components are just x over r and y over r, or in other words, x over square root of x squared plus y squared, etc. And what does that look like? So this is a good example of leveraging what we know and not doing it from scratch. So you could go back to a picture like this, and you could find your eraser, or yeah, there we are. We could just go ahead and plot directly, okay, what is the vector field here? What is the vector field here? And just do it in that sort of brute force way. But it's really good once you have an example of something that's related. This vector field is taking a vector field we already understand well and just changing by a scalar. What does that do? It doesn't change the direction. At any point, we're multiplying the vector that was already here, that was this guy, by a scalar. So that doesn't change the direction. So a really important thing, and one thing I'm trying to emphasize here, is separate out the plotting process into get the direction right and get the magnitude right. The direction is absolutely what we already had. It's radially outward. And then just figure out the magnitude. Well, the magnitude, it's not a hard computation. If you take a vector whose magnitude was going to be r, and you divide it by r, that's exactly how you get a unit vector. So this is called the unit radial vector field. Let me see if I can bring it back up. Okay. And so this is exactly like the previous one, but they're all turned into unit vectors. Okay. So that's an easy one to plot if you've already done the basic example. And you want to be on the lookout for that. Look for standard examples like the radial vector field and see if what you're asked to plot is a simple modification of that. Okay, so again, this is a good one. I wanted to use this to illustrate that idea of just changing a magnitude and not a direction. But honestly, it's not that interesting from the point of view of a flow or a force field. It's rather artificial. It is a good example of something where the components are bounded because they're all as unit vectors. So it's a bounded vector field, but it's discontinuous because if I look through here, it's unit vector pointing left, unit vector pointing left, unit vector pointing left, and then suddenly, boom, unit vector pointing right, unit vector pointing right. So it's kind of like a step function. In fact, the x coordinate, the x component is exactly -1, -1, -1, step to +1, +1, +1. So it's bounded, but it's not continuous. Okay. Now here's a really interesting one. I call it G2, which is a little bit weird. It's because it's related to three-dimensional gravity, or the Coulomb force of an electric charge, but it's the two-dimensional analog. So what we're doing is we're taking, very similar to what we just did, we take the radial vector field, and now we divide it by r squared. Okay, so that makes it actually get bigger as you go in towards the origin. Notice it's still radially outward, but now it's getting bigger as you go in. So again, this magnitude and direction division. We know the direction to point the arrows. If you do the calculation, we've taken that unit radial vector field that we just had and we divided the magnitude by r. So now the magnitude is 1 over r. And that's why it's getting bigger as you go in. And in fact, it's a little misleading here because it doesn't clearly say, because we're only doing a finite grid of evaluation points here, the magnitude actually goes to infinity right at the origin, and this is discontinuous and even unbounded at the origin. Despite that, it's an incredibly important example because it is the analog of, let's say, the electric field of a point charge. Okay, so it's the two-dimensional Coulomb vector field. You could relate it to gravity, but it's a little weird. I'm by convention, I'm having all these guys point outward, and gravity, of course, would point inward, would be an attractive field. In terms of flows, it's really important. What I claim, and we're going to have good evidence for this soon, I claim this is a flow of fluid from a point source right here at the origin. It's got a concentrated flow of fluid, and so the fluid flows out very, very quickly and then gets slower and slower as it goes out because it's got a larger region that it's spread out into. So this is a really good thing from point of view of flows. It's a concentrated point source. It's also, not only is it the analog of like a Coulomb field in 2 dimensions, it actually is exactly the right picture of an electric field if you have a uniform infinite line of charge that's perpendicular to the plane of the page or the screen here. I claim that's exactly what the electric field will be on the nose. And that's a standard calculation from basic electricity and magnetism, and we'll come back to justifications of why is that really true. But you can picture it that if I have a line of charge going through this point perpendicular to the screen, that you're going to get forces going outward, and they're going to get somewhat weaker as you go out. Exactly why in this pattern with the vector r over r squared, or with the magnitude being 1 over r, notice not 1 over r squared, that is worth further investigation. A couple more examples, or a few more examples. Don't want to make it too long, but these are all really good. Now we're going to go to swirly stuff. These guys, these three are really good examples, especially A, the radial one, and C, the G2 vector field. They're really good examples to talk about divergence. Vector fields that spread out, or if you put a minus sign in front of them, converge and come in towards the origin. Here we're going to look at things that have no divergence, that are not trying to spread out or come in, but are curling around to some degree, and sort of circulating is a really good word. We're going to use that in a technical way pretty soon. So here's minus yi plus xj. Let's do that by hand for a sec here. If I have like 2, 1, then P, I'm going to call this the pinwheel vector field, is minus yi plus xj. Okay, and that's going to be minus 1i plus 2j, or minus 1 comma 2. Okay, so it's going over a little bit and up a bunch. And what I want to notice is that if I dot product that with the radial vector field, which would just be 2, 1, I get 0. And in fact, in general, if I dot that with xi plus y, that's a y and that's a j, minus xy plus xy is 0. So I get something that's always perpendicular to the radial vector field. So that's why it's always going this way. And it's smaller when you go in. Okay. Okay, and notice the arrows are starting to overlap because I'm not being careful about the scaling. It looks prettier, of course, if we scale them down. Okay, and I do more points of evaluation. So notice this guy is pointing tangent to a circle at that's whose center is the origin because it's perpendicular to the radial vector. So that's really important. It's swirling around tangent to circles because it's perpendicular to the radial vector field. And if we calculate the magnitude, though, magnitude of this is y squared plus x squared all square root. It's the same. Okay, so the magnitude of this guy is r. One way to picture it is we're actually taking the radial vector field and we're just rotating all the arrows in place 90 degrees counterclockwise. So let's show that. Okay, so here's the radial vector field. Like at this point, it's going out with a sort of medium long arrow. And let's go down to the pinwheel. Right at the same place, it's going up and to the left, 90 degrees rotated with the same magnitude. Okay, so it gets bigger as you go out in a linear fashion. Minus y and x are both linear functions. Very continuous, definitely even differentiable, all throughout the plane, but swirling around counterclockwise. And the counterclockwise is because it's a minus here and a plus here. If you switch the plus or minus, it would go clockwise. But this is the more standard because our direction for positive rotation in mathematics is counterclockwise. So I call it the pinwheel vector field, not a totally standard terminology, but very reasonable. It is the motion of a fluid, but it's the motion of a very special kind of fluid, a frozen fluid. Because this is what happens if you take like an old-fashioned record or CD or anything, and you just rotate it as a rigid body. The linear speed is proportional to the radius, and of course proportional to the angular speed. And so this is exactly what's going to happen if it's a rigid body. So that's really important special case. I think I've mentioned everything else. Oh, what about as a flow? Oh no, that's as a flow. It's frozen fluid. It's not super realistic as a force field because again, whatever's creating that force seems like it would live at the center by the symmetry, but it's getting stronger as you go out. So it's not really a very realistic force field. It's a very realistic flow, but it's important that it's actually a solid thing rotating. So really quickly, here's the unit pinwheel. Just scale it down by r. It's not continuous, but it's still bounded. It's again more mathematically interesting than physically interesting. But once again, once you got the pinwheel in place, then it's not hard to see how to graph this. Graph the pinwheel, but just make sure you make all the arrows the same size. Okay, one last one. I know it's getting pretty long, but these are really worthwhile. The vortex vector field, probably my favorite out of all of these guys. So I'm taking, I should have, this is p over r squared. So I'm taking the pinwheel vector field and now dividing by r squared, very much like G2. In fact, it's just G2 rotated with all the arrows rotated in place 90 degrees counterclockwise. So this guy, because as you might guess from the name, this is fluid flowing in a vortex where the velocities are slower out here and then get very much larger here. And in fact, it's an idealized vortex where the velocities go to infinity right at the origin. So it's not continuous, not even close to differentiable at the origin. Nonetheless, a very important example. Okay, turns out in terms of physics, so like forces, it's not exactly a super common force field exactly, but it's the cross section of the magnetic field of a wire. Instead of a line of charge perpendicular to the screen, take a line of current, a wire perpendicular to the screen, and put a uniform current in it, and then take a cross section of the magnetic field. It's going to be strong, it's going to swirl around the wire, which is a fairly important thing to know about magnetic fields, and it gets stronger as you get closer to the wire in exactly this way, kind of like the G2 vector field, that as you go out twice as far away, it's 1/2 as strong. Notice that's not a 1 over r squared. That would be the analog in 3 dimensions. You get inverse square laws in 3 dimensions. We're going to talk about why that's true in terms of the vector calculus. So again, it's G2 with arrows rotated, and a really great example. So G2 and V are really the most important examples of all of these, but they're slightly more complicated than the others, which is why I didn't start with them.